Hello and welcome, guys, to the first video of our first unit for AP Calculus BC. So throughout this video, this one might be slightly longer. This is just sort of a forewarning, slightly longer than most of the videos that you will watch, just because it's our first one and it's almost going to be a little bit of a tutorial as to how to use these videos and kind of interact with them, and some of the language I'll be using and some of the techniques I'll be using to get you through them. So kind of bear with me for this one. I will try and make it as short as possible, but also want to make sure that I'm giving you enough information and going at an appropriate pace that you still understand what's happening. So this is where we'll start. The first unit is techniques of integration. And so I'm going to start off just kind of giving an overview of what that unit means, what is kind of going to be in front of you, and then we are going to get started with our first piece of content as well today. So the overview of the entire unit is basically this. So last year, you learned what an integral was, what it does, what its applications are. And then you also learned some techniques to how to integrate certain functions. So you learned the power rule. You learned how to integrate trigonometric functions, how to integrate exponential functions, logistic functions, inverse trig functions, so on and so forth. And then the last thing that you did, sort of the most advanced technique that you know right now, is integration by substitution. It's also known as U substitution. So that's really where AB stopped, right? That's kind of all the pieces that you know leading into this course. Well, what's going to happen is the beginning of this course is that there are still functions out there that we don't know how to integrate analytically. Okay, so analytically basically means by hand. What are those techniques that we can use to find the integral or the antiderivative of certain functions that don't necessarily follow the patterns or the types of functions that we saw last year? And so throughout this unit, there are going to be two new actual techniques. Again, so remember, integration by substitution is one of the techniques that you know. The first new technique is something called integration by parts, which is what we're actually going to do today. And then integration by partial fractions is the second technique that we'll learn. And then on top of that, we're going to learn two new applications of integration. The first one is kind of a mixture, I think, of a technique and an application. It has sort of more roots, I guess, within application and why it's used and why it exists. And that's something called improper integrals. And so we'll get to that. And then the last thing is something called arc length. So actually finding the length of a curve from point A to point B. What is the distance you would travel if you were actually kind of going along that curve? That'll be the last thing that we do. So we'll get into those more in depth when those videos come out. Did want to make just a quick note, though, and so I can't be more clear about this. We still want to know the previous applications. So from last year, right? So let's take a look. So here are the previous applications from AB that deal with integrals, area underneath the curve, accumulation problems. There's particle motion problems that you had to use an integral for. Volume of solid is a huge application for integrals. And then finally, solving differential equations. If you are uncomfortable with any of these, please, please, please come and see me. Come and find me, and make sure you get that taken care of, okay? Throughout this year, this is why I put it in the summer assignment. Throughout this year, I'm going to expect that you know either how to do this, or when we start doing an example, sort of a light bulb hits and you say, oh, yes, I remember that. I can do that. I know what you're talking about. If there's a point where we're doing an example or I show you something or there's a problem that comes up and you have no idea what's going on and it's based off of one of these applications, really anything, but for specifically right now, any of these applications, you have to come and talk to me, okay? Because we have to figure out, A, how do we fix that, or maybe B, is this sort of still the right path for you? Are you comfortable with doing all this and putting this all together? And so I want to make sure that you're okay and that everything that we're learning this year isn't just sort of piling on top of confusion that you might still have from last year. Okay. Everything we do this year definitely builds off of last year. So we need to make sure that last year's foundation is really strong. All right. So here are the 5 definitely need to know applications about integrals. Again, if you have a question about them, please let me know throughout these videos and throughout class and throughout your homeworks and so on and so forth. We'll be using these applications. Okay, so you will see them again. I'm not going to just leave it totally hanging dry, but I'm also going to expect you to know how to do them fairly readily. Okay, they will be a part of assessments. I can guarantee you that. All right, let's jump into it. So day 1 of our first technique of integration is called integration by parts. And so again, the idea here is that we are trying to figure out ways to integrate certain functions that we don't have any method for, right? We don't have a plan for it yet. And so what would those functions look like? You might be trying to figure that out. Well, integration by substitution, by and large, took care of a lot of composite functions. Okay, right? Remember f of g of x, and the derivative equivalent to that was the chain rule. Right? We said, well, integration by substitution is sort of the chain rule of integration. And so today we're going to look at functions that are typically products of 2 different types of functions. So 2 different types of functions multiplied together, or possibly quotients. So there's 2 different types of functions that are divided by one another, or one's dividing the other, rather. And in a lot of ways, this is kind of like the product rule of integration. It doesn't fit exactly. It's not always multiplication. There is some division, which we'll see. But in a lot of ways, this is sort of the product rule of integration. You'll see why I'm saying that in just a second when we kind of prove the formula. All right, and so listed below here, I just have 4 very quick ones, and we're actually going to take a look at these integrals, or something very similar to these integrals in the examples today. And so these are the types of integrals that you definitely need integration by parts from. And so if you're just kind of wondering to yourself, based off of what you did last year, and you're looking at these functions, start thinking to yourself, well, how would I integrate those? Do I know a way already? And the answer is no. But if you thought about it, x sine of x, well, maybe u substitution. Well, what would you make u equal to? Well, then the derivative doesn't exist for x or sine x in the other part of the function, and so that's not going to work. Well, it's certainly not just a power rule. It's certainly not just a trigonometric function. So you're kind of up a creek, right? And so with all of these, if you look at them, we, as of right now, don't know how to integrate them, and we're going to need to use something called integration by parts. So what is integration by parts? The reason why I said it's a product rule of integration is because the proof of it, or at least the way that we come to the integration by parts formula, is by starting with something we already know, which is the product rule itself. Now, why would I want to start with the product rule? Well, because a lot of the functions that we use in integration by parts for are products, right? So I quickly jump back. I see x multiplied by sine x multiplied by e to the x, the ln of x multiplied by dx. And so if I looked at ln of x divided by 5x to the third, that's really the ln of x over 5 multiplied by x to the negative third. So in fact, that is still multiplication. And so it makes sense to start with the product rule, because we actually already know what that is. We know that formula, and we're probably fairly comfortable with that. And so I know that the product rule says this. If I take the derivative of f of x multiplied by g of x, it's f prime g plus g prime f. Okay, we've used that a bunch of times at this point. Again, hopefully you know that and feel good about it. So, but I don't want derivatives, right? I want to talk about integrals. That's the whole idea. I want to be able to find the integral of 2 functions multiplied together. So what if, instead of the derivative, what if I took the integral of both sides, right? So I take the integral of the left-hand side, the integral of the derivative of f of x gx, and then that's going to equal the integral separately of those 2 other pieces on the right-hand side, right? The integral of a sum is really the sum of the 2 integrals. So all I did was take the integral of both sides and just kind of fixed it a little bit, cleaned it up a little bit. Okay, so now on the left-hand side, the next part, what happens right here? Well, that is the definition of the fundamental theorem of calculus, right? The integral of derivative, those 2 are inverses of one another. And so they're actually going to cancel each other out, for lack of a better term. And I'm going to be just left with f of x dx. Okay, so now on the right-hand side, I can't really do anything. Because those two things are multiplied, f prime and g of x, I'm not going to, it's not f of x because it's the integral of its derivative. That's not how it works. It's multiplied by something else. So I can't take just the integral of f prime of x and leave g of x hanging, or I can't just take the integral of g prime of x and leave f of x hanging. So those are actually going to stay the same for right now. And actually, I want to stop right here and just kind of look at, what else, what's happening, because remember the goal of the proof. The goal of the proof is to come up with a formula for a function that is actually the product of two different types of functions. And on this right-hand side, so if you look at this piece right here, I've actually got two integrals that are products of two different functions. I know I'm using f prime and g prime in both of those, but I mean, the derivative of a function is still a function, right? So technically, the integral of f prime g is the integral of a product of two functions. And the same thing with the integral of g prime f. So if I want to come up with a formula to figure out how to integrate the product of two functions, could I just solve for one of these integrals? And the answer is yes. Let me just get rid of this stuff real quick. All right. So if I were to subtract the second part over, so subtract g prime x of f to multiply by f of x over to the left-hand side. Now I've got f of x g of x minus the integral of g prime f of x dx equals the integral of f prime of x g of x. This part right here, this is the big thing, right? Again, my goal, integral of the product of two functions. That's the integral of the product of two different types of functions. Yes, does it seem like I'm complicating things because now that integral equals two functions multiplied together minus the integral of other two? I understand what it looks like right now, but this is actually really helpful. This is the whole proof right here. Because again, what was the goal? Integral of the product of two different functions. I have that, and I know what that equals. Well, if I know what that equals, that is the antiderivative. So now what I have to work at is actually just finding all the other pieces. So here is in this box piece, and throughout these videos, what you'll see is either conclusions or answers to problems. I'm going to box in an orange box, okay? So once I get there, that's kind of a big part, something you should absolutely write down or something you should have. That's our big conclusion, okay? Okay, so now the next part is really just the same, but I'm going to just kind of simplify the notation a little bit. And this is actually what you'll see in most textbooks. And this is how we're going to actually write a lot of our problems and do our notes and things of that sort. Okay, so this is not different. I'm just continuing the proof. We've actually already proved integration by parts formula. I'm just going to make it easier for us to use by simplifying the notation. Okay, because instead of using f of x and g of x, I'm going to use the letters u for f of x and v for g of x. Okay. If that's the case, well, the derivative of u is f prime of x dx. So I just took the derivative of f, which is f prime. And the derivative of v is g of x, or sorry, g prime of x dx. Okay, so just taking the derivative of u and v, which are f and g, and then I get those. Right. So now this formula, which we just found on the other page, comes slightly simpler. It says this: the integral of u dv, which is u is, or I'm sorry, that should say v. Give me 1 second. Okay, I apologize. I'm back, and I actually had to make just a quick correction. And so this is actually great because, like I said, this is sort of a tutorial video also. There's certainly going to be times where I make a mistake on the screen, and luckily I'm able to pause the recording and then just kind of fix it, and then I'll explain it to you if that happens. So I just made a quick notational mistake. So I'm just going to kind of start this over. Instead of u equaling f of x and v equaling g of x, I'm just going to flip those two, and that fits up with the formula. So if u equals g of x and v equals f of x, then du equals g prime and dv equals f prime. And now I'm going to simplify my notation from the previous screen. F prime g of x dx is really u dv, right? So dv is f prime dx, so f prime and dx, and then u is just g of x. And that's going to equal this part over here. And that is u times v multiplied by the integral of v du. All right, so v is f of x, and then du is g prime dx. All right, this box, this orange box, that's what you absolutely 100% need to know. Okay, so this is a big part. That is the bi-parts formula. That's the definite need to know. Let's jump into, well, how the heck do I even use this thing? Okay, so essentially, we're going to be starting with what I'm going to call like a normal function. So not a derivative of a function, just sort of a base function. And the other one is actually going to be the derivative of some function already. Okay. It won't look like that. I'm not going to tell you that that's the derivative of blank, or the problem won't be posed that way. But we're going to sort of assume we're starting with not u and v, which I think is what like is natural to think, but we're actually going to start with the function u, all right, so like your g of x function, and then we're going to start with the derivative of v, or the derivative of f. Okay, those two things are what's going to be multiplied together, and we need to figure out, what's the integral of u multiplied by dv. Well, if we have u and we have dv, okay, which we're actually going to be able to choose which one is which, and we'll get to that because that's an important step. But if we have those two pieces, we have u, we have dv, right? We have two functions right in front of us. Well, the formula says, okay, well, you need those two parts, but then you also need a du and a v, right, in order to complete this full formula together, right? And remember, here's the formula. So we're starting with u and dv. I need a du because it's at the back end, and then I need just a v itself, right? Because it's also as part of that final integral, and it's a part of the front part as well. So what am I going to do? Well, if I have u, du is just the derivative of that normal function, whatever I'm starting with, that base function, and then v is the integral of the other function. So once I have my two functions in front of me, it's the integral of this product of two different functions. I'm actually going to, as a setup piece, take the derivative of one of those functions and the integral of the other. Well, this is where choosing which one is u and which one is dv becomes very important, because there are some functions that are much easier to differentiate than others. There are some functions that are much easier to integrate than others. And in fact, there are some functions that we don't even know how to integrate yet. So I certainly wouldn't want to choose those to be the one that I'm integrating. So at this point, we know we have two functions. I know I'm going to have to differentiate one, and I know I'm going to have to integrate one in order to put all the pieces together into my bi-parts formula. So I honestly think the best way to go about this is probably to talk about just sort of like some typical approaches, and then we're going to go into an example. So my typical approach, and I just kind of said this, was, figure out which one is easier to integrate, set that one up to be dv. Typically, we want to be able to do that. We need to integrate something, so I need to be able to integrate whatever I'm integrating. So we need to look at that. Can I integrate it? Is easier to integrate. And then I also want to check which function might derive to a constant, right? So if I have an algebraic function, let's say like 2x, right, is an algebraic function, its derivative is just 2. Well, if I can derive something to make it really simple, like a constant, then that's going to make the rest of the formula really easy, okay? So a lot of the times those constants we're going to differentiate because they simplify really nicely. And then finally, honestly, for you to get the hang of this, there's just going to be some trial and error. You might make u the incorrect function at first, right? And then you're going to run into a problem eventually. The good news is that there's only two functions and two options, so you just have to go back and switch them. And so again, there might be some trial and error. Don't get too frustrated. We're going to work through some of them. Let's jump into an example. So this is the first one that you saw on the screen, right? And so I'm actually going to just quickly, just so you're not looking at a whole lot of stuff, right? I'm going to just box this up. And typically with these examples, again, as a tutorial, I'm going to kind of cover up some of it. And this will allow you to, if you're writing your own notes, which you should be, just to kind of take it slowly, write it piece by piece, and then also listen to me without looking at a whole sort of bunch of mumbo jumbo on the screen. So the first example is the integral of x multiplied by sine x. So if I'm looking at this, again, I have to decide which one is my normal base function, which one is the function that I'm going to integrate, right? That's already a derivative, right? So which one is u and which one is dv? Well, if you think about it, x is one of those algebraic functions. Making that equal to the one that you're going to differentiate simplifies the problem immensely, right? Because the derivative of x is just 1. If you look at sine, I know that the derivative of sine is cosine, right? The integral of sine is negative cosine. And that doesn't simplify. It just keeps flipping back and forth, back and forth, back and forth. Right? So typically, trigonometric functions, I almost never want to make equal to u because it doesn't simplify the problem at all. It just oscillates those functions. And again, I just want you to sort of mentally think about, what if you made the mistake of making u equal to sine x and dv equal to x? Okay, well then you would have to differentiate sine x to get cosine, which is fine. I mean, you're able to do that. But then you have to integrate x to the first, which becomes x squared over 2. So now you've complicated the situation more than you've simplified it. And that's not what we want to do. So in this case, for the first example, we're going to make u equal to x, dv equal to sine x, and see where that takes us. Once we make that initial decision to split those two up, I need to find the other pieces, right? So in order to do that, I'm going to take u equals x and take its derivative. Well, the derivative of x is just 1. I need you to note, and I need you to be very careful about this, right? You need to make sure you write this down every time. Du is equal to 1 dx, right? That dx is going to be there because you took the derivative of u. It's a very, very important piece that comes up later in the formula. So do not forget your dx whenever you take the derivative of u. On the other side, dv is equal to sine x, which we already said. Notice that I'm including the dx there because remember, when you take the integral, v equals the integral of sine x, we have that dx out there. So I have to include dx, okay? Because that is actually taking the place of everything that's inside of the original integral. So I've taken care of x and I've taken care of sine x dx. Well, the integral of v, which is sine x dx, is just negative cosine x, right? I know it's not a definite integral. I know I'm not adding a plus c because I'm not done with the problem yet. So at the end, if you're thinking, well, where's the plus c? We're going to take care of that random constant at the very end. So just keep it as negative cosine. So once I have those pieces, we're going to put the formula together, right? I know the formula in order to take the integral of that original function is uv minus the integral of v du. Well, I have all 4 pieces. Put them into the formula. So u is equal to x, v is equal to negative cosine x. Then I'm going to subtract the integral of v, which again is negative cosine x, multiplied by du, which is 1 dx. Okay, so that du with that dx, remember I said that's important? That is very important because it's part of that second integral, and I need that dx in that integral. Okay, so now this is actually really easy because the first part, x negative cosine x, I don't do anything with that. That is just part of the answer, right? So negative x cosine x is part of that answer. And then minus the integral of negative cosine. So I'm going to bring out that negative sign. I'm going to make it a plus. It just becomes plus the integral of cosine. And I know the integral of cosine is sine x. So now the final answer, putting it all together, negative cosine x plus sine x. And then finally, since it's an indefinite integral or an antiderivative, plus c. All right. So from the start, u equals x, dv equals sine x. Find the other 2 pieces. Once you find those 2 pieces, put it into the formula and let the problem work itself out from there. Okay. The goal is when you set up the formula, that second integral that you have inside of the formula, you should be able to do that integral, knowing everything you did from last year. Okay. So we're simplifying the problem by creating another integral that I already know how to do. All right. In this case, I already know how to take the integral of cosine. That's an easy one. Okay. Let's move on to example number 2. So example number 2, the natural log of x divided by 5x to the third. Well, I know that this is really 1/5 multiplied by the natural log of x. I'm sorry, 1/5 multiplied by the integral of the natural log multiplied by x to the negative third. Again, I had said that this is really multiplication, just kind of, it looks like division. I mean, it is division, but it's also multiplication, right? So this still works, okay, in the world of integration by parts, the product rule of integration. So now I think to myself, well, which is easier to integrate? And I've got two options, right? So my first two options, and yeah, I know this has been here for a bit, but I'm going to cover it just so you can listen to me. My first two options are the natural log of x. That's my one function. And then x to the negative third. That's my second function. Which of those is easier to integrate? Well, if you're thinking to yourself, well, what is the integral of the natural log of x? I hope you're stumped because you actually don't know the integral of natural log. You did not learn that last year. And in fact, we're going to learn that in the next example. So when I say which is easier to integrate of these two, you've only got one option because you only know how to integrate one of them, which is x to the negative third. And so x to the negative third is going to be the part that we integrate. The natural log of x is going to be the one that we make u, so we differentiate it. All right? And a little bit of a hint here, notice that we have one like algebraic function, it's a power rule function where 5x to the negative third or x to the negative third. And I know that the natural log of x differentiates to 1 over x. So now I'm taking an algebraic function and getting another algebraic function. And if I combine those two, that's just one singular algebraic function. So I'm now going from a natural or a logistic function and an algebraic function, and I'm going to simplify it to just one algebraic function that's going to integrate nicely. Okay, so again, we said our goal, which is easier to integrate, definitely the 5x to the negative third or the x to the negative third. So I'm going to make u equal to the natural log and dv equal x to the negative third. I'll differentiate the natural log, which is 1 over x dx, and then I'll integrate dv, which becomes negative 1 over 2x squared. Just to point out, if at any point you need to pause the video and just kind of look at the work and work it out yourself, obviously do that. That's a big benefit of having this video for your resource or learning from it, okay? Okay, now I've got these pieces. If I've got all 4 pieces, I'm going to plug it into the formula and let the formula do the work. So 1/5, so that 1/5 is kind of hang all the way on the outside, all right, because I took that constant out from the original function, multiplied by uv minus the integral of v du. Plug in my pieces. I know u equals natural log. I know v equals negative 1 over 2x squared minus v, again, which is negative 1 over 2x squared, multiplied by du, which was the integral of natural log, which is 1 over x dx. Again, remember I said, if I want to point out this piece right here, making u equal to the natural log, because its derivative is 1 over x, really brings this problem together, because I can combine those two pieces together to get 1 over x to the third, and that's one singular type of function, right? It's no longer a logistic and an algebraic function or a trigonometric and algebraic function. It's just one singular type of function that I can integrate nicely. So putting all the pieces together, the negative natural log of x over 2x squared, just combining that product from up here, right? Those are the same. And then I'm going to take out the 1/2 from the negative 1 over 2x squared. Again, that's negative. The negative in front of the integral will turn to a positive. And so really what I've got left is just the integral of 1 over x to the third, which I could, if you wanted to, change it to x to the negative third and then use your power rule. You don't have to, but you could. You would see that then equals 1 over 4x squared. And so just putting all those pieces together, I have my final answer. Again, take a moment, pause the video, jot some questions down if you have to, and just kind of follow those steps. Okay. So now, before we get into our third and final example, I just want to go over a quick rule of thumb. This is going to be really helpful when you're dealing with integration by parts problems, okay? The most important part of these problems is setting up which one is u and setting up which one is dv. All right, everything depends on that. The whole problem falls either or becomes successful or falls apart, all right, depending on which one you set. So there's an acronym that is very helpful. It does not work 100% of the time, but it works like probably 98 to 99% of the time. So this is really helpful. The acronym is Liate, or Liate, or Liate. I don't know, however you want to pronounce it. But what it does is this tells you which function to set u equal to. All right, and it's based off of the type of function that we're working with. So what does the actual acronym mean? The L stands for a logarithmic function. The I, and I'm just now realizing I said logistic a couple of times for natural log of x, and that's a logarithmic function, not logistic. Sorry, that's an easy mistake on my part. I is inverse trigonometric function. A is algebraic. T is trigonometric, and E is exponential. Again, this means what do I make u equal to? Okay. If you have a logarithmic function, make it equal to u. Natural log of x, that's logarithmic. I'm going to make that u equal to u. That leaves only one other option for dv, right? If you're working with an inverse trigonometric function, make it u. You know how to take the derivative of an inverse trig function. You do not know how to take the integral yet of an inverse trig function. So don't make that dv. From there, I'd make an algebraic function u, trigonometric function sine, cosine, and then finally exponential. And if you think about these last two, trigonometric and exponential, why would I not want to make those integrals? Well, again, it's because they are cyclical, right? They just kind of cycle back and forth. Sine, cosine, e to the x, e to the x, e to the x, e to the x, right? It doesn't get any simpler. So this is a good rule of thumb. Keep it in mind. It's going to be really helpful. Okay. So my last example is an interesting one, and I kind of mentioned this already. It is the integral of the natural log of x. And so if you're looking at it, you might say, well, Mr. Penola, it doesn't really follow that idea that it's a product of two different functions. Well, I do want you to remember that the natural log of x is being multiplied by dx. Right, so dx stands for the change in x, which is the width of those little rectangles that you would have made once upon a time to approximate the area underneath the curve. Those two things are being multiplied, and I can actually use dx as either part of one of the functions or one of the functions or pieces of the formula itself. And so according to our acronym, Liate, I'm going to make u equal to that logarithmic function, which is the natural log of x. If I do that, the only piece that's left is that dx. Okay, so I'm going to make dv equal to just dx, which again, I'm allowed to do. So this is nice. So u equals natural log of x, d equals 1 over x dx, dv equals dx. And then if I take the integral of just dx, which is really 1 dx, then it's just x itself, right? So the integral of 1 is just x. I've got my 4 parts. I'm going to plug it into my formula. The integral of the natural log is actually equal to x ln x minus the integral of x multiplied by 1 over x. That's a v du, which x multiplied by 1 over x, this piece right here, right, is really just the integral of 1 dx, which we've already run into in this problem. And so now I know the final answer is really just x ln x minus the integral of 1, which is x plus c. Okay, and so that is how you would do the integral of the natural log. So now that you know the integral of the natural log, that does not mean that you should ever use the natural log as your dv, right? Because again, you can see that really just complicates the problem further. All right, the integral of natural log is not simpler by any means. So we always want to make u equal to ln of x if we have that opportunity. So I'm actually going to cut this video off right now because this is just the content. The next video that I have available for you, which you should also watch, and you're going to be responsible for watching, is some try on your owns, okay? And I'll explain what that means, but really they're just more examples, problems that I'm going to give you that you should take just time to try on your own without looking at the solutions. Then I'm going to go over the solutions very similar to these 3 examples that I did. All right, just to give you a highlight, the try on your own number 1, which I'm going to call Toyo number 1, is x cosine x. So that's the first one you should try. Toyo number 2 is 3x to the 4th times the natural log of x dx. And Toyo number 3 is the inverse sine x dx. What is the integral of the inverse sine? Okay, and that's it. And your homework is going to be posted on my Malvern. Please take a picture of your work and use the My Malvern submission and send it in. Please take as clear of a picture as possible. Please make sure your handwriting is clear. If I cannot see it, that is going to be an issue. All right. Have a great day, guys. Again, make sure you watch the second video, which is the explanation of the try on your owns, and let me know what questions you have. Okay, guys, take care. Have a great day.